Hey everybody, Jake here, coming at you with another math lesson today. We're doing it live again today. It's part of our, weekly live stream, which we typically do every Monday night at 5 o'clock Pacific time. Today I wanted to go over with you, I've been talking on my channel recently about critical numbers quite a bit. So I wanted to kind of build on that topic, take it a step further, and show you some examples of finding local minimum and maximum values of functions. And the reason I say, building on critical numbers is because the first step in finding local maximum and minimum values of a function is to find the function's critical numbers. Obviously, there's going to be a bit more you're going to have to do on top of that, which I'll definitely be covering in this video. So if that's something that you want to learn a bit more about, be sure to stick around to the end of the video. And if you do get some value along the way, do me a favor and hit that like button. It's a huge help to my channel so I can keep making more videos like this. As always with these live streams, if you do have any questions along the way, just throw them in the live chat. I'll do my best to answer them live. If I can't answer them live off the top of my head, maybe I'll make another video about it some other time. So please, whatever questions you have, even if they're not on the topic of critical numbers or local extreme values, just throw them in the live chat and I'll do my best to help you out. This is also a topic that is covered on my free Calculus 1 study guide and my complete Calculus 1 package. If you want to check out those things, there is a link down in the description below. You can also just hop over to jakesmathlessons.com and check it out there. There's more info. But let's go ahead and jump into the examples that I have for you guys here. So first thing we're going to do is this example here. Find the local maximum and minimum values of this function. B of x equals 3x to the 2/3 minus x. So like I said in the intro, when you're doing these problems, the first thing you want to do is find the critical numbers. I have covered this in a handful of other videos, especially recently, but just kind of quickly to go over what that looks like, we'll start there. So first thing you want to do to find critical numbers is you're going to take the derivative of the function. So in this case, the function whose minimum and maximum values we're trying to find is this function here, b of x. We're going to need to take its derivative. So we're going to find b prime of x first. To do that, in this case, we can use the power rule to find the derivative of this first term. So we're going to move our power down in front, multiplying it by our coefficient. 3 times 2/3. The 3's are going to cancel, and we're just going to be left with 2. So 3 times 2/3 is 2. We're going to leave the x as x, and then we're going to minus 1 from the power. Well, minusing 1 from 2/3 would be exactly the same. Whoops. Not sure what's going on there. All right, well, sorry about that. There we go. All right, sorry about that. A little bit of a technical difficulty there. My eraser was not erasing. Okay, so minusing 1 from this is the same as minusing 3/3. So you need to have a like denominator when you're subtracting fractions. 2 minus 3 is -1. So 2/3 minus 1 is -1/3. Okay, so this is going to be the derivative of that term there. Then we have the derivative of minus x. Well, the derivative of x is just 1. So we're just going to get 2x to the -1/3 minus 1 is our derivative. So now when you're trying to find critical numbers, what you need to do is figure out where does your derivative equal 0 and where does your derivative not exist. So whatever x values make one of these two things happen is going to be a critical number, which is a spot where we could potentially have a local minimum or local maximum. So we need to basically take this equation, this b prime of x, and set it equal to 0. And then we also need to consider where does 2x to the -1/3 minus 1, where does this not exist? I'll come back to that part in a minute. Let's go ahead and start with this, where does it equal 0? So we pretty much just need to take this equation and solve for x. So first we will add 1 to both sides. Then we can divide both sides by 2. Then we can raise both sides up to the negative third power. Because if we raise a power up to a power, we multiply the powers. So we're going to get basically negative 1/3 times negative 3 is just 1. So that just leaves us with x to the 1, which is just x over on the left side of our equation. And then on the right side of our equation, 1/2 to the negative 1/3 would be the same as basically 2 to the third power, which would be the same as 8. So x equals 8 is going to be a critical number that we get from taking our derivative and setting it equal to 0. Now we also need to think about, where does this function not exist? Well, there's really only one possible thing that's going to make this function, or this, the derivative of our original function, our b prime of x, there's only one thing that's going to make this potentially not exist. Typically when you're trying to do this, or think about where a function does not exist, what you want to think about is basically what x values are causing you to basically break the rules of math. And what I mean by that is there's certain things that you just can't do, right? You can't divide by 0. You can't take the square root of a negative number. You can't take a log or natural log of 0 or a negative number. So you want to look for those kinds of things and basically figure out what x values would cause you to do one of those, breaking the rules of math things. So in this case, we don't have any square roots. We don't have any logs or natural logs, but we do have a fraction. And it doesn't look super obvious, but what you want to consider is that something raised up to a negative power is the same as 1 over that thing to the positive power. So 2x to the negative 1/3 is the same as 2 over x to the positive 1/3, and then minus 1. So clearly we have a fraction here, 2 divided by x to the 1/3. Basically, if there's any place where this denominator equals 0, that's going to cause us to divide by 0, which is against the rules of math. So we can't do that. So if there are any x values that cause this, that's a potential critical number that we want to consider. And in fact, there is, which would be x equals 0. So you want to be aware of this potentially causing some problems. One thing, let's see here. Okay, so basically these are the two kind of spots that we want to consider our critical numbers. One thing that you want to kind of keep in mind, though, is going back to our original function. Let's take just a moment and think about what is the domain of this function. The domain of 3x to the 2/3 minus x. Well, there's one kind of issue with this equation, and that is the fact that we have x raised up to a fractional power. Fractional powers are a little bit weird because if you're thinking about specific numbers raised up to a fractional power, right? Like we could take 5 raised up to the negative, or I'm sorry, raised up to the 2/3. We could figure out what that is. Or similarly, we could say -2 raised up to the 2/3, right? We could actually figure out what these numbers are. But in the context of a function, you want to be careful of doing that, because when we have x raised up to the 2/3, if we're trying to think of this as a function, right, we're trying to say x could be any number. This doesn't really work when we have negative x's. When you have a negative number, some number less than 0, when you have a negative number raised up to a fractional power. And the reason for that is kind of the idea of a function is you should be able to basically graph it, obviously, but you should be able to see, if you're thinking about a graph of a function, and let's think about negative x values. This, I'm just going to sketch an example of a graph. That's not what this looks like, but just in general, let's say you have some function where you're kind of graphing it for x values less than 0, right? Let's say you have something that looks like this. The idea here is that, especially a continuous function, basically x values that you plug in to this function and look at, what's the output of that function at that spot, x values that are near each other should give you some sort of result of a y value that's like somewhat in the neighborhood, right? And I mean, it's possible to have like a vertical asymptote, for example, where, going over a little bit in the x direction moves you up a lot in the y direction. But still, there is kind of a continuous path to get there. But when you talk about having a negative number raised up to a fractional power, it kind of creates some issues there in terms of the continuity of it. So you want to be very careful whenever you have a fractional power of your x or whatever your variable is in a function, because basically you're gonna want to ignore negative x values. The function isn't really going to exist for negative x values. So essentially all that I'm trying to say here is we don't want to consider x values less than 0. We only need to basically go to x equals 0. So the domain of our original function is all x values greater than 0. So just let me clear out some space here real quick. The domain of our original function is x greater than or equal to 0. We don't want to consider negative numbers because we don't want to take a fractional power of a negative number. So as a result of that kind of is where our critical number of x equals 0 is coming from, because we don't even really need to worry about what our function is doing for x values less than 0. We only really need to start at 0. So that was a bit of a tangent there, but the point I'm trying to make here is now that we've got our critical numbers, what we need to do is the first derivative test. Well, the first derivative test, how you always want to start that out, is just by drawing a number line. So let's just start by drawing a number line. And the only points that you want to put on your number line are your critical numbers. So in this case, we want to put x equals 0, x equals 8. Okay. A common mistake that I see people make when they're doing the first derivative test is they will always put 0 on their number line. But you want to be careful with that. You only want to put 0 on your number line if it's a critical number, or if you have a situation like this where your function is only defined for x less than 0 or x greater than 0. You don't always put 0 on the number line, only if it comes up as an edge of a domain or as a critical number. In this case, it is the edge of our domain of our original function, and also the edge of the domain of our derivative, because our derivative also has x raised up to a fractional power. We don't want to have negative x's. So once we have drawn our number line, in this case, we have a limited domain. This function and its derivative do not exist for all x values, right? In fact, they don't exist for x less than 0. So we can basically, what I like to do is even just scratch this out, like scribble it out like this, because that makes it obvious we don't actually want to worry about x values to the left of 0. And since our derivative does not even exist at 0, we don't even want to consider x equals 0 either. So basically we're going to start at basically x greater than 0, and we're only going to look at everything to the right of 0. So the first derivative test, what it says is you need to, once you've drawn your number line, you need to pick numbers that are in between each of these endpoints of your number line. So in this case, we've marked off 0 as an edge, and we've marked off 8 as an edge. So we have two kind of sections of our number line remaining here. We have x values between 0 and 8, and then we have x values that are greater than 8. So we have two domains here. X between 0 and 8, and x greater than 8. So again, we don't really want to worry. We don't want to pick these actual points. We don't want to pick 0 or 8. We need to pick some numbers in between them, or greater than our largest one or less than our smallest one. So these are the two kind of intervals that we need to test. What we need to do now is pick some number within each of these intervals. It doesn't matter what number you pick, as long as it is in between those intervals. So in this case, we have 0 to 8. Let's just test x equals, let's see here. let's just test x equals 1. It really doesn't matter what you pick. The only reason I said 1 is because that looks like it's going to be pretty easy to plug into your derivative, which is going to be our next step. And I'll get to that in just a second. So we'll say x equals 1 to figure out if this interval is increasing or decreasing. And then we need to pick some x number, which is bigger than 8. Again, doesn't matter what you pick. Just kind of looking ahead a little bit, what we are going to have to do is take the cube root of it. So let's go ahead and pick some cubic number, which the first cubic number bigger than 8 would be 27. So let's say x equals 27. Okay. So then once you've picked your x values, the first derivative test says that we're going to take those x values and we're going to plug it into our derivative. So we're going to plug it into b prime of x equals 2x to the minus 1/3 minus 1. So let me just write our derivative here real quick. Okay, so now what we need to do is plug in each of these numbers that we've selected into our function. So we're going to find b prime of 1, and we're going to find b prime of 27. So plugging 1 in, we're going to get 2 times 1 to the negative 1/3, again, is the same as saying 1 over 1 to the positive 1/3. And doing this, 1 to the 1/3 is just basically saying taking the cube root of 1. The cube root of 1 is 1. So 2 over 1 is 2, minus 1 is 1. So it doesn't matter what number you actually get. All that matters is whether this is positive or negative. So in this case, we have positive 1. So b prime of 1 is positive. Okay. So going back up here now to our interval, that tells us since our derivative was positive in this interval, our original function, b of x, is increasing. Okay. You want to always keep in mind the derivative of a function tells you about the original function's slope. So if the derivative is positive, the original function's slope is positive. If the derivative is negative, the original function's slope is negative, which just means that it's decreasing if it's negative, increasing if it's positive. Since b prime of 1 was positive, b of x is increasing at x equals 1. So our function is increasing within this interval. Okay, now we need to find b prime of 27. So that's just going to be, again, 2 over x to the 1/3 is 27 to the 1/3 power minus 1. 27 to the 1/3 power is the same as taking the cube root of 27, which is 3. So this is going to give us 2/3 minus 1. 2/3 minus 1 is negative 1/3. Again, it doesn't matter exactly what number we get, but negative 1/3 is negative. So b prime of 27 is negative. So if the derivative is negative, that means the slope of the original function is negative, which means it's decreasing. So the first derivative test tells us that we have a critical number at 8, which means that it may be either a local minimum or a local maximum. Applying the first derivative test to that confirmed that since it's increasing to the left and decreasing to the right, we have something on our graph that looks like this, which is going to be a local maximum. So we have a local maximum at x equals 8. So x equals 8 is a local maximum. If we wanted to then actually find the maximum value, the local maximum value, we would take x equals 8 and plug it back into our original function up here. So we would just find b of 8 to get our actual maximum, local maximum value there. And I'll leave that for you to do. It's pretty much just plugging it into a calculator from there. So I'll leave that for you. So that's it for that first question. I'm not seeing any questions in the live chat. If you are getting some value out of this video, do me a favor and hit that like button down below. It's a huge help to my channel so I can keep making more videos like this and keep doing live streaming and keep helping you guys get through calculus. All right. Cool. Let's go ahead and hop on to the next question here. I got another one for you. So next question here. Find the local maximum and minimum values of f of x equals ln of x to the fourth plus 27. Okay, I'm going to go a little bit quicker through this problem since I just kind of went a little bit slower through that last one. But let's go ahead and go through the same steps here. So the steps, whenever you're trying to find local minimum and maximum values of a function, you're always going to start with the critical numbers. So to find critical numbers, first thing you need to do is find the derivative of your function. To find the derivative of this function, we're going to have to use chain rule, which is one of the topics on my free Calculus 1 study guide. If you want to check that out, there's a link down in the description below. I also talk about chain rule, local minimum and maximum values, critical values. All that is covered also in my complete Calculus 1 package. Link to that is down in the description below as well. But the derivative of this is going to require chain rule, which says that we're going to take the derivative of the outside function, leave the inside function alone. So in this case, the parentheses make it pretty clear what we want to consider our inside function and our outside function. So what's in the parentheses will be our inside function. Our outside function is the natural log part of it. So the derivative of the outside, leave the inside alone. The derivative of natural log of x is 1 over x. So if we're taking the derivative of the outside, leaving the inside alone, we're going to get 1 over our inside function. And then chain rule says we need to multiply that by the derivative of our inside function. The derivative of x to the fourth can be found using the power rule. Bring the power down in front, leave the x as x, and minus 1 from the power. The derivative of a constant is 0. So our derivative is going to be 4x to the third over x to the fourth plus 27. Okay, once you find your derivative, the next thing you need to do in order to find critical numbers is to figure out where does f prime of x equal 0 and where does f prime of x not exist. In this case, we have a rational function. Our derivative is a rational function, which just means that we have a polynomial over a polynomial, a fraction where you have the top and the bottom of the fraction just being polynomials. When you have a, f prime, your derivative is a rational function like this, it's pretty easy to split up and find critical numbers because all you have to do, the only places where a fraction like this is going to equal 0 is where the numerator equals 0. So if we just look at 4x to the third and set that equal to 0, that's going to be the only places where this whole fraction as a whole equals 0, because 0 divided by any number is 0. And the only places where f prime of x might not exist is wherever the denominator equals 0, because we don't have anything else besides a fraction that could cause us to accidentally break the rules of math. There's no square roots, there's no logs in this function, but there is a fraction. So we need to be careful of dividing by 0. You cannot divide by 0. So if the bottom of a fraction equals 0, that means you're dividing by 0, which is against the rules of math. So what we can do is just take the bottom of our fraction and set it equals 0. Now we have these two equations that when we solve them will give us all of our critical numbers of our original f of x. So to solve this for 0 or for x, we can divide both sides by 4 and then take the cube root of both sides. So x equals 0 is going to be one of them. And then for this one, we can, again, let's basically just start to move everything over and get our x all by itself. So we'll minus 27 from both sides. X to the fourth equals negative 27. Take the fourth root of both sides. And notice what happens here. We're taking the fourth root of negative 27. You cannot take an even root of a negative number. So this actually does not exist. This does not give us a real number. So this equation does not have any solutions. There's no places, no x values where x to the fourth plus 27 equals 0. So as a result, we don't get any critical numbers from trying to figure out where f prime of x does not exist. But we do have this critical number x equals 0. So x equals 0 is going to be our only critical number of this function. Okay. The other thing that we want to be careful about is are there any places where f of x or f prime of x does not exist, or any restrictions on the domain? We already figured out there's no places where f prime of x does not exist, but are there any places where f of x does not exist? In this case, we don't have any fractions or even roots, but we do have a log. We have a natural log. What you want to keep in mind is that you cannot take the natural log of some number that is 0 or negative. So we need to be careful to make sure that x to the fourth plus 27 is never negative. Well, raising something to an even power is always going to make it positive, or unless it's 0, 0 to an even power is just 0. So x to the fourth will never be negative. So if we have some non-negative number plus 27, that's always going to be positive, which means this function, what we're taking the natural log of, is always going to be a positive number. So this function will exist for all x values. So the domain of this function, this original function, is all real numbers, right? There's no x values that are going to cause problems. There's no x values that we're not going to be able to plug into f of x. So as a result, really the only points that we want to put on to basically do our first derivative test to figure out where our local maximum and minimum values are is the one critical number of x equals 0 that we got. There's no restrictions in the domain of f or f prime, and the only critical number we got is x equals 0. So those are the only things that you want to put on your number line when you're trying to do the first derivative test. You're always going to start, that was not a very good line. You're always going to start your first derivative test by drawing a number line. Once you draw your number line, the only points you want to put on it are the places where you have a critical number or where you have restrictions in your domain of your original function. In this case, there are no domain restrictions. We only have a single critical number at x equals 0. So be careful. In this case, x equals 0 is a critical number, and that's why it's on our number line. A very common mistake I see people make is that they will always put x equals 0 on their number line. But the only reason you'll want to do that is if x is a place where your original function has issues with plugging x equals 0 into the original function, or if it's a critical number. In this case, it is. So that's why it's here. Okay, so now you can see this number line has basically been split into two pieces. We basically just split our number line for all x values less than 0 and all x values greater than 0. Those are the two domains, or basically, areas of x values that you want to test now using our first derivative test. The first derivative test says that we're going to take some number within each of these sections. So let's just say x equals -1 and x equals 1. Okay, it really doesn't matter what number you pick as long as you pick one number from each section. In this case, x equals -1 is in this section, x equals +1 is in this section. So then what we're going to do is we're going to take each of those numbers that we've selected and we're going to plug it into the derivative. That's why it's called the first derivative test. We're going to use our first derivative. So we're going to go back to f prime of x, this function right here, and we're going to plug in x equals -1 and x equals 1. So let me just start with copying this derivative down here. Okay. Now we need to plug each of these into our derivative. Let me move this one actually a little bit further over here. Okay. So plugging in -1 into this is going to give us 4 times -1 cubed all over -1 to the fourth plus 27. Plugging in +1 is going to give us 4 times 1 cubed over 1 to the fourth plus 27. Okay. Now to simplify these, -1 cubed is -1 times 4 is -4. -1 to the fourth power is +1 plus 27 is 28. And then that's going to simplify to negative 1/7. Okay, and then let's simplify this f prime of positive 1 over here. We're going to get 1 cubed is 1 times 4 is 4. 1 to the 4th is 1 plus 27 is 28. So this is going to simplify to positive 1/7. All right. And if you are getting some value out of this video so far, do me a favor and hit that like button down below, please. It's a huge help to my channel so I can keep making more videos like this. And still not seeing any questions in the chat. If you do have any questions along the way, feel free to throw those in the live chat. But let's carry on. So now that we have plugged in our critical numbers, or not our critical numbers, I'm sorry. Now that we have plugged in the numbers that we chose to the left and the right of our critical number, what does this tell us? Well, the first derivative test tells us that since f prime is negative at this x value, that means the slope of our original function is negative at that x value, because the derivative of a function always tells you about the slope of the original function at any given point. So in this case, if we know that f prime is a negative number at x equals -1, the slope of f must be negative at x equals -1. So if the slope of f is negative, that means it's decreasing at that point, right? So our function f is decreasing for all x values within this interval over here, okay? Similarly, since we know that f prime is positive for the x value of x equals 1, that means that since f prime is positive, the slope of f is positive. So the slope of our original function f is positive, which means it's increasing. So basically, our function f is decreasing to the left of x equals 0, and it's increasing to the right of x equals 0. So if we're decreasing to the left and increasing to the right, we have a local minimum right there, because it's coming down and then going up over there. So this critical number of x equals 0 is a local minimum of this original function. Now, if we wanted to find the actual minimum values, we could just simply plug in x equals 0 into our original function. And figure out what that value is. 0 to the 4th power is 0, plus 27 just leaves us with natural log of 27, which you could just plug into a calculator to figure out what number that actually is. But that would be a local minimum of this function. And that would be the only local minimum of this function. So that's it for that problem. Still not seeing any questions in the chat. If anybody does have any questions, go ahead and throw them in there real quick. That was the last problem I had prepared for you guys. So if you did get some value out of this video, go ahead and smash that like button down below for me. And go check out my free Calculus 1 study guide and my complete Calculus 1 package. The links to both those things is down in the description. I do talk a bit more about all the topics we just covered in this video in both of those resources. So go check those out. I think you'll find them very helpful. Should get a lot of use out of them. Should really help you, get your grades up and do well throughout the full term for calculus. So go check those out, and we'll wrap things up there. Thanks for joining, everybody. Have a good rest of your night. See you next week.